We're going to be talking about integrated rate laws. We've been talking about rate laws already, but the important word now that distinguishes these rate laws is the word integrated. Up until now, the rate laws we've been discussing have been what we'll now refer to as differential rate laws. So integrated and differential rate laws are simply two different mathematical forms of the same chemical rate law, same chemical phenomenon, but two different mathematical ways of looking at it. So if we look at a generic reaction where we have a reactant A forming just general products, remember that the rate laws we've been looking at, the differential rate laws, these all describe, that'll be shown on the left here, these all describe how the rate varies with the initial concentration of reactant A in this case. Now I've changed the word rate and I've made it delta A over delta T, but remember that's just another way of saying rate. Okay, and the reason I changed that is because in the derivation, as we go from differential rate law to integrated rate law, I have a separate video that explains how these are related to each other. It derives the integrated rate law from the differential rate law. If you took or are taking calculus, then the words differential or derivative and integrated or integral will mean something to you. And you don't have to understand how to go from one to the other, but if you're interested in it, there is a separate video that shows how to do that. So the important part here, chemistry-wise, is that this is just a mathematical operation that we're doing when we integrate, and so we get a new form of the rate law. So instead of rate as a function of reactant concentration, what we see on the right in the integrated rate law is concentration of our reactant as a function of time. That's the lowercase t. So we all know that since A is a reactant, the concentration will decrease over time, but this form of the rate law describes how it decreases over time. First order reactions look like this, where rate is equal to the rate constant times A, concentration of A, the initial concentration, to the first power. That's why it's first order. If we integrate that, we get this form of an integrated rate law. And then, of course, second order, this is the differential rate law that we're used to looking at, where the rate is proportional to A squared, to the squared of the initial concentration of A. That's why it's second order, because it's the power is the second power. So if we integrate that, we get this form of a second order rate law. Now, if we think about zero order reactions, remember that a reaction is zero order in A when the concentration of A has absolutely no effect on the rate. So the rate equals K times A to the 0 power, and of course anything to the 0 power is a 1. So that reduces the expression to rate equals K. Over here on the right, I'm just putting it at the top. So if we plot concentration of A along the y-axis and time, lowercase t, along the x-axis, then what you see is that you get a straight line if it's a zero order reaction, and the slope is equal to negative K. The y-intercept is equal to the initial concentration of reactant A. So that's what that sub-zero means. That means at time t, what was the initial concentration of A? Now if we look at a first order reaction, we have rate equals K times concentration of A to the first power. That's why it's first order. And if we integrate that, we get the natural log of A will vary as negative K times t, or time, plus the natural log of the initial concentration of A. That's A sub 0. Now if we show the plot on the right, that's the same equation above it. Natural log of A equals negative kt plus the natural log of A sub 0. What you're looking at below that is the plot of natural log of A along y as a function of t, lowercase t, time, on x. And you can see that because the equation above it is a straight line equation, if you plot natural log of A as a function of time and you get a straight line, then that implies that that reaction is first order. The slope is equal to negative K, and the y-intercept is equal to the natural log of A at time 0. Now the left-hand graph is meant to show you that if you thought it had been a zero-order reaction and you had plotted, instead of natural log of A, you plotted just the concentration of A as a function of time, you would not get a straight line. You would get what we call an exponential decay, where it decreases rapidly at first and then it levels off later. So that is not linear. If we move on to second order reactions, this is the last one we're going to look at, and you can see that rate varies as a function of k and as a function of a to the second power. That's why it's a second order reaction. If we integrate that differential rate law, then what we get is what's shown here on the right. 1 over concentration of A equals kT plus 1 over the initial concentration of A. If we take that equation in the lower right hand of your plot that, you can see that's the plot on the right. So if we plot 1 over the concentration, in this case we have a specific reactant, nitrogen dioxide. We're plotting that as a function of time, and you get a straight line. The slope of that line is k, and the y-intercept is 1 over a sub 0, as you can see in the equation at the top. On the left-hand side, that would be a plot that you would make if you thought this was a first-order reaction. And you would see that you don't really get a straight line. It's almost straight, but it's not really straight. It's an exponential decay where it decreases quickly and then it levels off. So this is to summarize. The differential rate laws are on the left. Those are the ones we're used to looking at. And if you integrate each of these, you just get a different form of the same rate law. So instead of monitoring rate as a function of reactant concentration, what we're monitoring is how the reactant concentration changes over time as the experiment progresses, as the reaction proceeds to the right.